In this video, we're going to learn how to solve differential equations using Laplace transform technique. So this is a very powerful technique and you can solve many order differential equations, not just like first order, second order. You can actually simplify any problem much quicker. And the main technique is using the partial fraction method. So I would recommend that like you watch the special partial fraction technique for Laplace transform video before you start watching this one, because then you will see that how things can happen. So let's look at the problem like this. So let's say we're gonna solve, for example, this differential equation. This is second order this second order constant coefficient differential equation. So we have a y double prime plus by prime plus cy equal ft. Ft is like given function. And we also need two initial conditions. So there are, because it's second order. So you have given y0 equal y naught. Y0 means it has to be evaluated at 0. This is like very important fact, because the reason is when you look at the Laplace transform, you remember that you can take the integral from 0 to infinity. So because of that, we have a 0 in the bottom. So this is like a many question many students have, why it is 0. There is coming from the uh, bottom limit. And also there should be another condition, y prime 0 equal y1. So y1 is just another number, just a number. Okay, so this is a question we try to solve, and we also solve like higher order differential equations in certain examples. So if you have a problem like that, there are four major steps to solve. So uh, the the first step is take the Laplace transform of the differential equation. So first we take the Laplace transform of the differential equation, the entire equation, the both sides, left and right. That's the first step. And the second step is we're gonna plug in the initial conditions. We're gonna plug in the initial conditions and then try to simplify a little bit. So that's the second step. The third step is we're going to solve for ys. So ys is the Laplace transform of yt is a solution. So we assume ys is a Laplace transform. So we're going to solve for that, for the ys in the Laplace domain. And then final step is we're going to take the inverse Laplace transform of the ys one. So we can take the inverse Laplace transform of ys to get yt. So that's the idea. And then how to find the inverse Laplace transform? So major techniques are, we can use the partial fraction method. That's the main step, main method, and then also sometimes some special divisions. And you can see I have done those kind of things in the special partial fraction method video. So you can watch them before you start. So it will be, you will see that like those things are very well connected. And then also we use tables, so common tables, and also you can find a link for the table of Laplace transforms. And those two are like a major tools for this. So, and then also like when you try to take the Laplace transform, you need to know how to find the derivatives, how to what are the Laplace transform derivatives. So that means this is something really important. So what we do, we can assume that ys is the Laplace transform of yt. So that's like a main assumption. So we just assume that ys is the Laplace transform of yt, and then we have these results. So for example, the first derivative. So Laplace of the first derivative is ys minus y naught, and then only the s has for the first term, and then everything else has a negative, and also evaluated at 0. So those are like common things that you can see. Only the ys is appear in the first term. So the second one. So second one is y double prime, which is equal to squared ys minus sy naught and y prime 0, y prime 0. So you can see first term has a squared term, and then everything else is negative, and also evaluated at 0. And only the first term has the ys term, and the same pattern repeats. So in general, so if you have yn, so you can see yn has a sn, and ys appear only the first term, everything else is negative, and then all of them are evaluated at 0. Everything is evaluated at 0. Okay, those are the common things that you can notice. Okay, now let's try to use these ideas to solve several differential equations. So we're gonna go with like major type that you should know when you try to solve using differential using the Laplace transform technique. So let's look at this first, the problem. So we have solve y prime plus 3y equal e to the 4e with the initial condition y0 equal to, so you can see it's given at 0, and we only need 1 because it's first order. Okay, so let's try to see how we do. So I'm going to go step by step in this problem. So write step by step. Okay. So, uh, so let's say the answer. So what we do, so we normally write this on let ys equal the Laplace transform of yt. That's like the first one we write. Okay. And then what we do, we go step by step. The first step, what was the first step? Take the Laplace transform. So taking the Laplace transform, you can say like LT. So Laplace transform. Since the first one, let's try this. So taking the Laplace transform of the differential equation. So what happened? So when you take the Laplace transform, you can write it like this. So it's the Laplace transform of y prime plus 3y equal the Laplace transform of e to the 40. So we take the Laplace transform of both sides. Now we know that the Laplace transform is a linear operator. So because of that we can break this. So we can break this into two. So it's the Laplace transform of y prime plus 3 is a constant. You can pull it out. And then we can write Laplace transform of y, which is equals to Laplace transform of e to the 40. Now we can use all those formulas. So you can see that. So one thing we remember that we know that the Laplace transform of e to the at. So what we normally call the eat function, which is 1 over s minus a. So it's like a very interesting result to remember because it appears everywhere. Sometimes you can remember this with a positive way or negative way. Idea is just switch the sign. That's the easiest way to remember that. Just switch the sign. Plus become minus. Okay. So let's plug in them now. So that means the first one going to be s ys minus y naught. So that's the first one. Plus, so that's coming from the first one, the derivative part. And the second one going to give you 3ys equal, and then you can see there are no other terms, just the ys. And then the other side, we can use that eat function property. So it's going to be 1 over s minus 4. So that's the first step. Next, what we do, we can plug in the initial conditions. So let's go to step 2. So we can substitute initial conditions. So we have we have ys minus, and you know that the first initial condition is y0 equal 2. So that means this one going to be 2, because y0 equal 2. And then plus 3ys, there are no conditions for that side, equal 1 over s minus 4. So that's the second step. And then what we do, we can do a little bit of simplification here, and you can see that you can write this one. You can combine the first terms. So the first terms are the y term. So you can, when you combine, you can see that you can write this one as plus 3 ys, and also you can actually move the 2 to the other side. You can move this 2 to the other side. So you can write this one as 2 plus 1 over s minus 4. You can write it like that. Okay, you can always do that. You move everything else to the other side. Everything else to the other side. We only leave the y term on this side. The third step, solve for ys. That's third step. So we start with the same equation. What we normally, like this is general theory. What we normally do is try to simplify the right hand side. So so we can put a 2 over 1 and then do the cross multiplication and write it like that. So you can just simplify this one using this 3 arrow argument. So you can multiply this way, then multiply that way, then multiply this way, the 3 arrows. So let's do that. So that means we're gonna get here 2 times s minus 4 plus 1 and then divided by uh, s minus 4. So that means if you simplify, what you get is, you can see you're going to get 2s minus 7 over s minus 4. Now what we do, we can divide both sides by s plus 3. So after we divide by this, the factor of ys, so you can see you can write this one as ys equal to s minus 7 over, you can see s plus 3, you divide by that factor both sides, so you get s minus 4. That's what you get. So the last step, so after now we solve for ys, now what you need to do is just invert this one. So find the inverse Laplace transform of this one using any technique that you know. So what we normally do, most common technique is to use the partial fraction method. So let's do that. So the first step is take the inverse Laplace transform ys. So we start with the ys expression. So we have ys equal to s minus 7 over s plus 3 s minus 4. So what we do, we do a general theory. So general theory is we try to find the inverse. So what we do, we use the partial fractions. So use partial fractions. So to do that, what we're going to do, we're going to start with the expression on the right side. So we can write it like this. So it is 2s minus 7 over s plus 3 s minus 4. So what we do, we write this one as identically equals to a over the first factor s plus 3. So you can do that when you have distinct linear factors. So here what we have is distinct linear factors. So that's like the first case or the easiest case. And the next one is b over the other factor, which is s minus 4. So we write the partial fraction like that. Sometimes we make a mistake, we write this as equal to the other side. That's not actually exactly correct. It has to be an identity. So it is like 3 lines because those are identically equal. We use the properties of identities. Okay, now what we normally do is we're going to multiply both sides by the denominator of the left side. So once you do that, you get this. So you can see that when you multiply, what will happen is you cancel the bottom term and write the other one. You cancel the bottom term, write the other one. So that's what happens always when you multiply like that. So you do not write the one in the denominator, but write the rest. Okay, now what we do, how to find them? So we actually use the interesting argument. So what the argument is, we try to cancel the other term. We try to make the other term 0. So for example, let's say you want to find a. So if you want to find a, your goal is to make the other term 0. You want to make this term 0. So the easiest way to make this term 0 is you want to take the factor 0, which you can do if you plug in s equal negative 3, because that's a 0. You plug in the 0. Once you plug in the 0, that second term goes away, you get the b. So that's the idea. So it's a substitution as much as you can. So let's do that now. So as we discussed, so we're going to find a first. So we're going to substitute s equal negative 3. So we're going to substitute s equal negative 3, which is the 0 of the other term. So when you do that, you get 2 times negative 3, negative 7 equal, now we write equal, a. So what we get here is negative 3, negative 4. You can see the other term is simply 0. So this can give you the value of a. So you can see if you solve for a, you get 13 divided by 7. So it doesn't really matter what numbers you get, and this is the number you get. And then similarly, to find b, what we're going to do, we're going to make the first term 0. You can see to make the first term 0, you can find s equal 4. So that's the idea. So substitute s equal 4. So when you do that, you get 2 and then 4 minus 7 equal, first term is 0, the second term going to give you b 4 plus 3, and that is going to give you the value of b, and you can see which is 1 7. Now we can plug in those values, so we can write it like this. So we can write it like that. So we normally put the numbers in the numerator. So just to isolate, exaggerate what the term is, because we want to see what is in the denominator mostly. So we write it like that. Okay, now what we do, we take the inverse Laplace transform of this one. And then, so we can write it like that. We know the yt is the inverse Laplace transform of ys. And then, so we can substitute the partial fractions. And then we use one of the major properties of the inverse transform. We know that that's also linear. So we can break this down to 2. So that's one of the big help here. So again, because of L inverse is linear, so we can write the numbers outside of this one. Just we only write what we need inside. And then let's recall this result. So we know this result. We know that the Laplace transform of the e function, the e to the at function, it is 1 over s minus a. Because of that, so if and only if, you can write the inverse. So if it is the inverse of the other side, inverse of 1 over s minus a, which is going to give you the e to the at. So we go backward. So we use that property. Because of that, you can invert each term now. So that means you can write this one as, so the final solution, which is yt, which is equals to, so you can say from the first one, you're going to get 13 over 7. And because of s plus 3, in this case, a is negative 3. So it's going to be e to the negative 3t. First one. Second one, you can see it is 1 over 7. So this is going to give you e to the 4t. So that's the answer. And so that's the idea. So these are like all the steps and how you can use these steps to solve the problem. So let's look at the next one. So as the next one, we have y double prime minus 2y prime minus 3y equal 1 plus e to the 2t. y0 equals 0, y prime 0 equal 1. So go step by step. So first what we do, take in the Laplace transform. So take in the Laplace transform. So we can write this one as Laplace transform of y, second derivative minus 2 y prime minus 3y, and on the other side we have 1 plus e to the 2t. So we can recall a few things. We know the Laplace transform of 1, Laplace transform of 1, which is according to the table, is 1 over s. And as before, Laplace transform of e to the at, which is 1 over s minus a. Okay, so now we're going to use a table and we try to write one by one. So what we do, we're going to substitute. We can take the conditions first. So if you expand this one, now you can write this one, first one. So the first derivative going to give you this one, which is s squared ys minus sy0 minus y prime 0. So that's what the formula says. So this is how it always looks like. So that's the first term, y double prime. So let's go to the second term, which is minus 2. We normally write this outside. So let's start writing the second one. So second one is s ys minus y0. That's the second term. The third term, which is, you can see minus 3, which we write outside, and we only get ys in this one. So I just do exaggeration. So we just write this one as ys. So we only get ys for the last term. And on the other side, you can see this also equals to, we have a 1, that means 1 over s. And then we have e to the 2t, so that means 1 over s minus 2 according to the formula. Okay, that's what we have on the other side. So now what we can do, we're going to plug in the initial conditions. So we know that the y0 is 0, so that means this term is 0. And also this term is 0. And then y prime 0 is 1. So this is 1. So let's substitute those and collect the ys terms. So we're going to collect all the ys terms together. We have 1, 2, and 3. So we're going to collect them and we can write it like this now. So after substituting and collecting the conditions, you can write it like this. So it is s squared from the first term minus 2s from the second term minus 3 from the third term, and the ys, which is common. And then we're going to move all the conditions, all the other terms to the other side. Everything else you move to the other side. So that means, so there's no s term, but we're going to move this 1. So negative 1, so it's going to be positive 1. So it's always happen because of the negative signs. And then we already have 1 over s and 1 over s minus 2. That's what we have. We isolate the ys term on this side. Now what we can do, we can simplify this one. So just take the common denominator and simplify. So we can write it like this. So so the first one, actually you can see you're going to multiply s with s minus 2. Second term you only have s minus 2 is missing. Third term you only missing s. Everything divided by s minus 2. That's what you get. And if you simplify, you can see this simplifies really well. So s squared, you get a squared term, and s term get cancelled out, so you get a negative 2, and they divided by s minus 2. So that's what you get for a ys. That's what you get for the right hand side. Now what we can do, we can divide both sides by this factor, and you can first see that this factor has you can factor this. So the two factors are one is s minus 3, the other one is s plus 1. So we can divide by that factor both sides. So let's do that. So when you write it, there's no real order, but what we normally do, we write from smaller to larger with the magnitude. So we have 0, 1, 2, 3. So we just write it like that. I mean, there's no real order. Now what we do, we can invert this one to find the yt. So to do that, we're going to use the partial fraction method. But this time we can use a special case of the partial fraction method, especially when you have distinct linear factors. All the factors are distinct. What we do, we use a shortcut, what we normally call the cover-up method. So let's use the cover-up method and see how we can get the answers really quickly. So we use the cover-up method for this case. And the cover-up method. And also you can find a link in the description if you need to know more about that. You can learn them with a few more examples. So we again, normally we start with the regular partial fraction expression. So we can write a one term for each. So we can write this one as like this, one term for each. So for example, a over s, like that. So we have all three terms like that. Now the goal is to find a, b, c and d. So let's use the cover up method. So what's the cover up method? We're actually going to cover up the term that you're going to find. So just the denominator. So let's say you're going to find a. If you're going to find a, we're going to cover up s. And for the rest of the expression on the left side, we're going to plug in the corresponding zeros. In this case, the corresponding zero is s equal 0. You plug in s equal 0 for the left side and you directly get a. So that's the idea. So you're going to cover up the denominator term in that expression, in that term, and find the corresponding 0, plug in the 0 to the left side. So you just get the, so you can still use a normal argument, but this is like a quick way to get it. So this is what happened. So we remove the s term and get the rest, and then what we do, we're going to plug in the 0. What's the 0? S equal 0. That's the 0 of the a term. So we're going to plug in that, and then we're going to get this one. So we're going to just plug in these values. So you get negative 2 from the numerator, 1 from the first factor, negative 2 from the second factor, negative 3 from the third factor. And if you simplify, you're going to get negative 1/3. So that's the value of a. So you can similarly find the other values as well, so like this. So b equal 1 over 12, and similarly you can get c and d like this. So you get c equal negative 1/3 and d equals 7/12, using a similar argument. Now what we do, we're going to plug in these values to the ys expression like this. So we have ys. Now what we do, we use the inverse of 1 over s minus a expression to find the find yt. Now we're going to use the common e expression, and then take in the inverse Laplace transform. We can have the answer like this, where we use the fact that the Laplace transform of 1 is equals to 1 over s. That's how you get the first term. So this is how you solve a equation with distinct linear factors quickly using the cover-up method. So let's look at the next one. So as the next one, we have y double prime minus 2y prime minus 3y equal 4e 2t, y 0 equal 1, y prime 0 equal 0. So we can use the same method. So taking the Laplace transform and using the initial condition, we can write it like this. So we have first term is s squared over ys minus s y0 minus y prime 0, the first term, and then the next two terms, so it is negative 2, we have s ys minus y0, and the third term, which is negative 3 ys. On the other side, you can see that there's the eat function, so we can use the property here. So we know that e to the at equal 1 over s minus a. So because of that, you can write this one as 4 s minus 3. Now what we do, we're going to plug in the conditions. So y0 equal 1, you can see this is 1, and then y prime 0 equals 0, so the second term is 0. So you can write it like this now. Now we can simplify the right hand side, just taking the common denominator, we can write it like this. So we get this one once you simplify, and then also you can see that there are two factors here. So what are the factors? One is s plus 1, the other one is s minus 3. The next step is we can divide by that factor both sides and write ys like this. Solving for ys, we have, so you will see that s minus 3 gets squared here. So that means we have a special factorization when you have repeated linear factors. So we can write it like this now. So you get b over s minus 3, and we know that we discussed this one. When you have repeated linear factors, the next one, which is x minus 3 squared, which is also has the same format as the previous one. So these two have the same format. So all of them follow the format of the smallest one, smallest power, 1 in this case. Okay, now what we can do, we're going to find ABC. We use what we call the hybrid method for this one. That's the quickest method to get this one. So let's multiply both sides by the common denominator on this side. So we can write it like this. So then we get this one, and you can see that always you do not write, you cancel the term in the denominator, write the rest. So this is what you get. So what we do, we use the what we call the hybrid method. So what's the hybrid method? You're gonna use a substitution as much as you can first. So let's do that. So we're going to go with the substitution first. So let's say you can substitute. You can say c equal negative 1. So once you plug in negative 1, and you can see these two terms get cancelled out. So then you get the a directly. So that means, so it is 1 and plus 5 plus 10 equal a times, when you plug in negative 1, you can see that this is going to be negative 4 squared, and all the other terms are 0. So this is going to give the value of a. So a equal 1. Similarly, you can substitute c equal 3 to get the value of c. So once you solve, you get c equal 1 again. Now you can see that you cannot plug in any more values. So what we do next is we can use the coefficient technique. So we can go with the highest coefficient. We can equate, because this is an identity. Since it's an identity, you can equate the coefficients. You can do that in an equation. Equation, you cannot equate two sides, but in an identity you can equate the coefficients of the two sides. So we're going to go with the highest one first. So we're going to go a squared. So we write like this. The coefficient of a squared is 1 on the left side. On the right side, you can see that you're going to get a squared term when you square s and multiply by a. So that means the coefficient is a of the squared term, and you also get a squared term when you multiply the first terms with b. So that means the coefficient is b, and you can see that there are no other terms. So that means since we know the value of a, you can find the value of b. In this case, value of b is 0. So that's it. So you can find a, b, c values. So you're going to plug in them now. So you can write it like this now, because of b term is 0. Now how to find the inverse of this one? So for that one, you need the first shifting property. So remember the first shifting property. It says this. So it says that the Laplace transform e to the minus at ft. If you have minus sign, what happen is you simply get s plus a. So you find the Laplace transform of the original function, replace s with s plus a. That's exactly what we have here, but a equal negative 3 in this case. And you can see we have 1 over s squared. That means the corresponding function is t. When we have squared means t. So that means, so we have this. So we know that the Laplace transform of t is 1 over squared. So that is the function here, if t is t. So that means you can write the solution like this if you take the inverse. So if you take the inverse of term by term, the first one is going to give you e to the negative t. The second one is going to give you t e to the 3t, because here the function is t. So that's what you get from the first shifting property. So let's look at the next one. Hurry. Now you will see that this expression is slightly different from what you see earlier. So you have a special term here. We have s minus 3 squared. We didn't see a term like that. So if you get something like that, what we're going to use? We're going to use the first shifting property. So FSP. So let's see how we can do that and get the final answer now. So what is the first shifting property says? It says that if you take the Laplace transform of a product, which is e minus at, we normally go with the minus sign, which is the most common one, and which is going to give you, we find the Laplace transform of the original function, in this case ft, and then replace the s by s plus a. That means opposite sign. So that means it's going to be f. So you replace s by s plus a. That's how we do. So that is what we call the first shifting property, and you can see the sign says plus is opposite sign, minus a plus a. Okay, so let's see how we do this now for our problem. So what we have is this. So we first take the inverse transform. So taking the inverse transform, we have yt, which is the inverse of the two terms. So we can write like this. For the first one, actually we can use the eat function property. So we have this e to the at equal 1 over s minus a. So because of that, you can write the first term directly, which is because here a is a negative 1, so a equal negative 1, so that means e to the negative t. That's the first term. For the second term, what we're going to do, we notice that the original function, in this case the original function is, so you can see we're going to ignore the negative 3 term, so it looks like s squared, so 1 over s squared. So 1 over s squared means we know that, so if you take the inverse of that, inverse of 1 over squared, so which is going to give you t from the table, we know that that's a t function, because if you take the transform of t, it is 1 over squared. So that we first figure out. So how we did that? We ignore the negative 3, just look at the general form. So general form is, you can see, is a 1 over s squared. That's the general term. So we just look at the general term. So 1 over squared. That's going to give you t. So that means now we use the first shifting property. So we figure that out. It is the t function. So what you're going to do, you write this as a multiplication now. So it's going to be t times a e term. To get the e term, you can see that a equal negative 3 in this case. A equal 3 in this case. So a equal 3 in this case. So because of that, you can write the final answer. It is a t times, because that's what the first shifting property says, the function times e to a, so in this case 3, so that means a negative 3t. So that's the benefit of writing in this form. So that is the answer, and that's how you get the answer for a problem like that, so using the first shifting property in the middle of a problem. Okay, I also want to give like a little comment on something, how we actually find the partial fraction. So there's another shortcut. Even when you have repeated terms, there is a shortcut. So let's talk about that quickly. So we can do this. So how we can find quickly those ABC for the same problem. So we have this. So now the question is how to find ABC. So you can see that you can use the cover up method to find the A and the largest one. So you can find A and the largest one. Largest one means C. So you can find these two using the cover-up method like this. So A equal 1. And then similarly you can find C also. So you get C equal 1 also. Now the question is how to find B. So you can see that B you cannot just plug in a value and get because you can see that because S minus 3 factor gonna repeat, and also that's the same factor in the denominator. So but we're gonna do a nice trick here. So the goal is to try to create a 1 plus 1 or minus 1 in the denominator term. Because if you do that, then you can directly get the B value. So that's what we do. Because after you find these values, then you go for the next one like that. So you're gonna try to make the denominator either plus 1 or minus 1. When you do that, you get, so for example, you can plug in SC equal 4. When you do that, is a B over 1. That means you can find B. And there also, the next one also going to be S minus 3 is 1. So C over 1. So we get something like this now. Substitute S equal 4. So that's the trick. So we get this. We know that A equal 1. So it's going to be 1/5 from the first term. The second term, we don't know B is a B over 1 because that's how we pick S. And then next one, C also 1. So it is 1 over 1, which is 1. So now you can see, you can find B directly. So you can see that if you simplify, you get 6/5 on this side and 6/5 on the other side as well, plus B. So this says that B equal 0. So that's how we use the cover-up method in a slightly modified way to find all three values quickly. So we did not use the hybrid method like a substitution coefficient equation, equating coefficient technique for this one. So we just use the cover-up method, and then we try to make the denominators either plus or minus 1. So then we can find the values directly because it doesn't give you like a much harder values. Okay, so so let's look at the next problem. So we have y double prime plus 4y equal 5 e to the negative t, y0 equal 1, y prime 0 equal 3. So we use the same argument. So we take the Laplace transform of the equation. So we get this term by term. Next, we use initial conditions. And then you can take all the y terms in one side and move everything else to the other side like this. Next, what we do is we solve for ys. That's like standard procedure. So let's do that. So do that, what we do, we divide both sides by s squared plus 4 and we write it like this. This time, like normally, like when we get something like that, we normally simplify the right hand side before we divide. But this time actually we don't want to do that. The reason is you already know what is the inverse transform of this one, because we can split them into two and write the two. So you already know this one. So because of that, we only going to find the partial fraction of this part. So you can see that. So this is like something you remember. So in this one, we only going to find the partial fraction of the second term because we already know the first one. So let's do that now. We know how to write the partial fraction for the first term, which is going to be a over s plus 1. What about the second term? Second term has a quadratic term, s squared plus 4. So when you have a quadratic term which is degree 2, so we know that this is degree 2. So what the general theory says, the numerator has to be degree 1 less than the degree of the denominator. That means this has to be degree 1. So degree 1 polynomial means the numerator has to be bs plus c. So that is the format because this is of a degree 1 polynomial. So this is something you want to remember, like what happened when you have a quadratic factor in the denominator which is irreducible, you can break it. So then the numerator has to be degree 1 less than the degree of the denominator. This argument always works. It doesn't matter what you have, even the repeated one you can also do that, but there are special simplification arguments when you have repeated terms. So when you have repeated terms, what we normally do, you can show that all the repeated terms follow the format of the smallest degree term, so which normally like constant term most of the time. So that's so you can show that's how it works. You can simplify it. It's just algebra. But here you cannot do that because you cannot break the denominator. So this is a special format. Now we have three unknown, so we can standard argument to find them. So what we normally do, we're going to multiply both sides by this factor. So let's do it. Now the question is how to find ABC. So we normally use the hybrid technique for this. What's a hybrid? You try to use the substitution method as much as you can first, and then you use the coefficient equating. You're gonna equate all those coefficients. So let's do that. So we're going to do substitution. So you can see that you can make this term 0 by plugging s equal -1. So let's do that. So when you do that, you can see that you get 5 on this side. This is A. When you plug in -1, 1 square is 1, so it's 1, and 4, and you can see this is 0, and because of that you get A equal 1. So now in the value of A, and you can see that that's it. You cannot find any more using substitution. So next what we do, we're going to go with the coefficients. We always start with the highest coefficient. So highest term. So in this case highest term is s squared. So it's s squared. And you can see that there's no squared term on the left side, so it is 0, coefficient is 0. And how to get a squared term? You get a squared term with when you multiply these two, so the coefficient is A. And also you can see that when you multiply the first terms, bs and s, you get a squared term. That means the coefficient is b. So you really don't want to expand this one and waste your time, because you can just think like how you get it, because you don't need all the terms, you only need some terms. Okay, now since we know the value of a, you can find b, which is just the negative a. So that means it is -1. So b equal -1. Now we go with the coefficient of the next lower term, which is s. So you have to go in the order. So you can see that there's no s term, which is 0 again. How to get s terms? And you can see that only way to get s term is you multiply c and s. That's the only way you can get s term. Oh, actually, and there's one more, and then the bs and 1. So there are two ways to get it: bs and 1 and c and s. So that means if you do bs and 1, so the coefficient is b, and then if you do cs, coefficient is c. Since you know the value of b already, c is simply -b, so that means 1. So we get all three coefficients: a equal 1, b -1, c 1. So now what we do, we plug in there, plug in these, and try to simplify ys. So let's do that. So this is what we get after you plug in the values for ABC. And now you can see that there are interesting things. You see, this is the same denominator. Because of that, this s and the negative s get cancelled out. And then also you can add 3 with 1, which is going to be 4. So then you can write it like this. You get 1 over s plus 1 plus 4 over s squared plus 4. Now what we can do, we're going to invert this using formulas. And you may recall these few formulas. We have these important ones. So first one says Laplace transform of cosine omega t, which is s over s squared plus omega s squared. And the sine omega t going to be omega over s squared plus omega s squared. And you can see both have a plus sign. And the hyperbolic ones have a minus sign. And then the first shifting property, which is e to the minus at, ft equal fs plus a. But what happens if ft equal 1? If ft equal 1, you get the famous the eat function. So you can write it like that. This is the special case of the first shifting property. When you have ft equal 1, this is what you get. Okay, now we can use these to write the answer like this. And for the second term, you can see that the omega equal 2, because 4 equal 2 is squared. So what we do, we pull a 1, 2 out, and we put 1, 2 inside and write it like this. Now you can see that they are in the right format. For the first one, you can see that a equal -1. And for the second one, you can see that omega equal 2. So that means the final answer going to be, for the first one, it is e to the minus t. And from the second one, which is 2, sine 2t. So that's the final answer of the problem, and using these identities. Okay, so let's look at the next one. Suppose we have this special problem. So here we have few things. One thing is, you can see that the coefficients are like not like you don't have 1 in front of y double prime term. So, and then also you will see that it is not easy to factor this one. So when you see something like that, what we normally do, we try to use the completing square argument. So let's see how the math gonna work. So we first take the Laplace transform as before. Next what we do, we plug in the conditions and we see the y0 equal 1 and then uh, y prime 0 equal 1/2. So you get this one is 1/2. So let's plug in those values and simplify a little bit. And we only leave y term on this side and then move the other terms to the other side. So we can write it like this. And then you divide by this factor. And you can see that factor doesn't have any linear factors. So we can write it like this. So we get this one. Now, since the denominator term doesn't have nice factors, what we do, we can use the completing square argument. So let's see how it's going to work. So the goal is to try to recreate a square term in the denominator. So let's see how it can be done. Idea is this. Look at this identity. So when you have a plus b over 2 squared, what happened? You get a squared and twice the product and multiply by twice the product. So that means when you multiply by 2 and multiply the two terms inside and multiply by 2, you get ab, and then you also get b over 2 squared. So this is actually argument. This is like main formula when you want to use the completing square argument. So what happened here is, so you have a b term, that's the coefficient of a, and you just put the half of that here. Half of that here. So that's the idea. Any sign, plus or minus, whatever sign you put it there. So we can use the same idea here. So what we do first is, we actually trying to pull out a 2 from the denominator. So 2s minus 3. So you pull out a 2 from the denominator. And then when you do that, you can write it like this. You can say squared. When you pull out, you get negative 2s. So we leave some space here and move the phi to the other side. We just to separate that. Now what we do, we're going to see what is the special term that we need to add. And you can see this is negative 2. So we're going to go, according to the argument, we need the half of that, which is negative 1. And then we're going to square that. And you add that term. So let's add that. So it is 1 in this case, because it is negative 2 divided by 2 and you square. So which is negative 1 squared, which is 1. So 1 is the term. So add 1, but when you add 1, you see what happened. You're actually not adding 1. Because of the 2 outside, you are adding 2. So just to cancel that, you subtract 2 from the other term, just to match them. Now we do the algebra. So you can see, when you do that, so the idea is, when you add that special term, the term inside the parenthesis is going to be a complete square. So that means you can write this one as 2s minus 3 divided by, this is 2s minus half of the coefficient, which is negative 1, and squared. So this automatically happens, and then plus 3 in this case. So that's what you get. Now we are not done yet. So what we're trying to do, we try to recreate s minus 1 in the numerator as well, so that we can use some formulas. So what we do here now, so we can write this one as 2. We try to replace s with s minus 1. So it's a similar argument. When you do that, and you can see, you are actually subtracting a 2. So just to cancel that, we add a 2. So that means we write this one as next. So we had already plus 3, but you subtract, because since you subtract, in this case actually it's a negative 3. So since you subtract, just to cancel that, you add a 2. So that they cancel each other. Okay, and then the denominator is the same. So which is 2s minus 1 squared plus 3. So let's simplify this a little bit. So then we're going to get this one. Actually, next what we can do is we can simplify this, and also we're going to pull this 2 out. So let's do that. So it is 1/2. We take it out from the denominator, and the numerator you're going to simplify. So in the numerator is going to be 2s minus 1 minus 1. And in the denominator, now what we have is, we have s minus 1 squared. That's exactly what we need. And plus, since you pull out a 2, it's going to be 3/2. That's what we get. Okay, now what we do, we're going to split them into two. And remembering the formula for sine and cosine, we can split them like this. So we can write it in this form. So the first term, because of the 2 and the 2, they cancel each other. So you are going to get s minus 1 over s minus 1 squared plus 3 halves from the first one. From the second one, actually we do some little bit of algebra here. You can see for the second one, the term omega squared is 3 over 2. So that means we need the square root 3 over 2 for the numerator. So we're going to divide and multiply. You're going to do multiply and divide in this case. So we write this one as 1/2. That's coming from this. And then we have s minus 1 squared plus, you can write this one as little exaggeration, 3 over 2 square root square. That means your term that you need is 3 over 2 square root. You need that. So what you do, we write this upside down so they can cancel each other. So we do that. We multiply and divide, in other words. So now you can see they are in the right format. So we can use the first shifting property and the sine cosine formulas to get the answer now. So we can use these two. So we have the Laplace transform for cosine, sine, and the first shifting property. So let's see how we can get the answer term by term. So by the linearity we can write it like this. And then also for the second term, it simplifies to 1 over square root 6. And now what we can do, we can identify these with the formula that we have. And you can see the first one, which is a s over squared with the plus sign. S over squared with the plus sign means it is related to the cosine. So we figure that out. This is a cosine. We simply ignore the negative one term. Just figure out what is the form. Form is a cosine. Cosine and also omega. In this case, in both cases, you can see that which is square root 3 over 2. So that's the omega. So from the first one and using the first shifting property, we first write the function. So you can see the function in this case is simply cosine omega is square root 3 over 2 times t. Now the shifting part in this case is of s minus 1. So that means it is a equal minus 1. Since a equal minus 1, you need to multiply by that e to the negative at term. So which is going to be in this case e to the t, because a equal negative 1. That's how we do it. So we first write the form and then multiply the shifting part. For the second one also, let's see what is the format. You can see it is a constant. It's omega over a squared type. Omega squared means, and with the plus sign, this is a sign. So we do the same thing now, which is minus. So it is sine. You can see square root 3 over 2 t. And then the shifting part is again s minus 1. S minus 1 means a equal negative 1. So you can see a equal negative 1. So that means if you plug in that to the first shifting property, you get e to the t. So you multiply by e to the t. So that's the idea. First we figure out what is the type, and then we multiply by the form. So in this case, you can see you just multiply by the ft. So there are no shifting here, just the ft. That's why we write it like that. And then you multiply by the extra e term. So that's how we solve a problem using the completing square technique. So let's look at the next one.